Now we will introduce the Laplace transform, which is a mathematical tool that will help us to solve differential equations and to analyze dynamic systems in general. The Laplace transform is a mathematical operation that takes an equation from being a function of time and transforms it into being a function of the Laplace variable s. And the way that the operator works is this integral definition here. So you can imagine that we have some time function f of t. We plug it into this integral and we solve this integral, and the result is a new function that's a function of s. To try and give you a little bit of physical intuition for what this operation is it's the Laplace transform is a generalized version of the Fourier transform, where this Laplace variable s has meaning as a complex frequency, or it can be interpreted as a complex frequency. And that won't make a lot of sense right now, but it's something that we will come back to later in the semester. In general, we don't really need to understand this operation so much. We're just going to use it. It's just going to be a tool that makes some mathematical operations simpler, which is the reason that we like it, and we're going to bother learning it. In general, we will never solve this integral. Instead, somebody else has taken some of the more common time functions that we might encounter, put them into this integral, solved the integral, and then tabulated the results. So we don't actually have to solve this integral, we can just look up the functions in a table. So here is the beginning of a table with a list of several time functions. There is a more complete table in your book on pages 18 and 19 that list the time function and the corresponding function in the Laplace domain. These functions are particularly important, so we're going to sort of look at them in a little bit more detail. The first function has a special name. It's called a unit impulse. It's represented by the Greek letter delta. And this function, it's an idealized function that's 0 for all time, except for at time equals 0, it has an infinite magnitude. And so this, nothing in real life has this exact behavior, but it approximates basically signals that have very short duration and very large magnitude. So you could sort of imagine, maybe a hammer strike or something like that being approximated by this unit impulse. The unit means that the area underneath the curve is equal to 1. If you took this unit impulse function and plugged it into the integral expression on the previous slide and solved that integral, the result would be equal to 1. And so that's what the Laplace transform of the unit impulse is. Another important function that has special notation is the unit step. So the unit step is 0 for all time less than 0, and then at time equals 0, it steps up to a constant 1. So that's what this notation means. This 1 of t represents a unit step. Sometimes you'll see other notations like u of t, but in our book and in this class we're going to use 1 of t. And so be careful, this doesn't mean 1 times t. It is the unit step function. Again, if you take this function, substitute it into the integral, and solve the integral, the result is 1 over s. So the Laplace transform of the unit step is 1 over s. Another important function that has its own name is something called the unit ramp, which is just t. And so what that is it's basically a straight line that has a slope of 1 and a y-intercept of 0. So you can imagine it as y equals mx plus b, where the slope is 1 and the y-intercept is 0. And this is a picture of that, where the slope of that straight line is 0. In general, all of the time functions that we are going to deal with, we're going to presume are 0 for time less than 0. And so that's what's represented here. This straight line, instead of continuing backwards, at time 0, it's equal to 0 for time less than 0. Sometimes, in order to make this more explicit, they'll actually multiply the function by the unit step, because the unit step is 0 for time less than 0 and it's 1 for time greater than 0. So if you multiply by the unit step, you will be multiplying everything before time equals 0 by 0 and everything greater than time equals 0 by 1. Again, if you solve the integral for this time function, you'll get a Laplace transform of 1 over s squared. The next element is t to the n power, so this applies to t squared or t cubed, a parabola, a cubic, and so on. The general form of this is n factorial. That's what that exclamation point means. So 5 factorial, it means 5 times 4 times 3 times 2 times 1. So it's n factorial divided by s to the n power. The Laplace transform of an exponential, e to the minus at, is 1 over s plus a. The Laplace transform of a sine wave of frequency omega is omega divided by s squared plus omega squared. The Laplace transform of a cosine of frequency omega is very similar. It has the same denominator, but the numerator is equal to s. So it's not my expectation that you completely memorize this table, but these more common functions you probably want to get a little bit familiar with. The table of Laplace transform pairs on pages 18 and 19 are limited. Sort of obviously, you cannot list every function, every time function that exists. So what we'll do is we're going to learn a few important properties that allow us to take the Laplace transform of a wider range of functions by building up more complex functions from the simpler functions in the table. So you could sort of imagine the previous slide, we could build up functions from exponentials and sinusoids and constants and so on. A summary of these properties that we're going to go over and some additional ones can be found on page 20 of your book. So the first property is linearity. The Laplace transform has the property of linearity, and that means that you can split the Laplace transform over addition and subtraction, and if you have constants, you can factor those constants out front of the Laplace transform. And so that's what we've done here. We've split it over the addition, so the Laplace transform of f plus g is the same as f of s plus g of s. And similarly, when we have a constant, we can bring that constant outside of the Laplace transform. And these two properties follow directly from properties of integrals. You may remember that if you had a constant in your integral, you could factor it outside of the integral. Or if you had an integral of a summation, you could split the integral over that sum. An important thing to notice, which often trips people up, is that you cannot split the Laplace transform over multiplication or division. So the Laplace transform of f times g is not equal to f of s times g of s. And again, this is something that you may be able to remember by thinking back to the properties of an integral. If you had an integral of a product, you would have to use integration by parts or the substitution rule or something like that in order to evaluate the integral. Two other important properties of the Laplace transform are when you take the Laplace transform of an integral and when you take the Laplace transform of a derivative. And so if you take the Laplace transform of a single integral of f, the integral of f of t, you get the Laplace transform of f of t divided by s. And if you have a double integral, you get the Laplace transform of f of t divided by s squared. You also have these additional terms which depend on the initial value of the integrals. Oftentimes these are 0. Often the integral doesn't have an initial value. An exception or an example that you might be able to think of a physical system would be, if you were analyzing a circuit and the capacitor had some initial charge on it, you could imagine that as being an initial buildup in your integral. But in general, these are generally equal to 0. So the sort of the take-home point is that integration in the time domain becomes division by s in the Laplace domain. And this is something that you maybe saw in the intro course when you were using Simulink and you used an integrator block. The integrator block was 1 over s, and that's where this comes from. That s is the Laplace, and it's driving home this, or it's based on the fact that division by s in the Laplace domain is integration in the time domain. Conversely, if you take the Laplace transform of a derivative, instead of dividing by s, it's multiplication by s. So if you have a single derivative, you multiply by a single s. If you have a second derivative, you multiply by s squared, and so on. If you had a third derivative, it would be s cubed, etc. You also have these extra terms that are based on the initial conditions. So if you have a first derivative, you also have to subtract f of 0. If you have a second derivative, you have to subtract s times f of 0, and you have to subtract f dot of 0. So it's like the initial condition of the function and the initial condition of the derivative of the function. And so these two properties exemplify one of the main reasons we like the Laplace transform. It turns differential equations and integral equations into algebraic equations. So instead of doing integrals, we divide by s, and instead of doing derivatives, we multiply by s. In general, we like to do algebra better than we like to do calculus. Another property is multiplication by an exponential. And so if you have a function, f of t, and you multiply it by an exponential, that causes the Laplace function to be shifted. So it causes a multiplication by an exponential in the time domain, causes a shift in the Laplace domain. And the reason that this is important is it's important for sort of damped response. And so we saw this earlier for our mass spring damper system. When our characteristic equation had complex roots, we ended up with a damped response, a damped sinusoid. And you can imagine lots of systems act like this. You pull the mass back and let it go, and it oscillates with a decaying amplitude. And so many physical systems have a response that's damped, and so it's important for us to understand how to take the Laplace transform. So let's go ahead and try this example where we have an exponential multiplying a cosine. Just recall that we cannot split the Laplace transform over multiplication. So the Laplace transform of this product is not equal to the Laplace transform of the exponential times the Laplace transform of the cosine. Rather, we have to use a property like this property number 4. So matching this function to that property, we can see that the cosine is our f of t. It has the place of the f of t. And if we look back to our Laplace transform table, we can see that if we look up a cosine time function, we can see what the corresponding Laplace domain function is. So taking the Laplace transform of a cosine, or of our f of t in this case, we get that our f of s is s divided by s squared plus omega squared. Going a step further and using this property 4, the multiplication by the exponential causes a shift in the Laplace function. So in essence, we're going to take our f of s, which we already found, and everywhere that there's an s, we're going to replace it by s plus a. And that, in turn, is the Laplace transform of that whole function. An important thing to notice, or to point out at this point, is a bit of terminology. So the roots of the denominator of a Laplace domain function are called poles. So if we took the denominator here and we set it equal to 0, and we found the roots, i.e. we solved for s, we would get that the poles are equal to minus a plus or minus j omega. And so something to notice is these poles correspond to the roots of the characteristic equation of a corresponding differential equation. So when we solved a differential equation and we looked at the roots of the characteristic equation, the real part of the root told us the rate of decay, and the imaginary part of the root told us the frequency of oscillation. And that's the same thing that we get from the poles. So again, this isn't something that I expect you to remember completely right away, but it's something that we're going to hammer as we go through the course. Here is another property which is basically the opposite of the property in the previous slide. So in the previous slide we had an exponential in the time domain causing a shift in the Laplace domain. The opposite is true here. A shift in the time domain causes multiplication by an exponential in the Laplace domain. Time shifts are important to understand in order to analyze time delays. So you could sort of imagine that our original function f of t looked like this. The time shifted version, f of t minus tau, or f of t minus a, has the exact same shape. It's just shifted in time. And again, sometimes we include multiplication by the shifted step to capture the fact that we're multiplying by 0 for all time less than tau or less than a, and we're multiplying by 1 for all time greater than tau or greater than a. The reason this property is important is because time delays are common in control systems. You could imagine that you're trying to base your control off of a sensor reading that's been sent over the CAN. And so there's scheduling of the signals on the CAN. There's the time that it takes for the signal to travel across the network. And so by the time you get that sensor reading, it is delayed, it is old. And so we need to understand the effect of that on our controller's performance. Similarly, sometimes we base our control based on a sensor that's downstream of the thing it is we're controlling. For example, we may be trying to control our engine based on a sensor in the exhaust. And so the exhaust is in essence, it's old. The combustion process happens and the exhaust travels some way to the, back to the catalytic converter or whatever, and that transport takes time. So again, we're trying to do our control based on old information, and we need to understand the effect of that. So let's go ahead and apply the various Laplace transform pairs and properties that we've just learned to solving this more complex Laplace transform. So, we've got this sort of more complex function that maybe doesn't exist in our table, but we can understand it using the various properties we just introduced. So the first thing to recall is that we in general will assume that our function doesn't start until time equals 0. So our function is 0 until time equals 0. And so what that means is this constant 5 we in essence can treat like a step. It's as if it were 0, and then at time equals 0 it jumped up to 5. Okay, so that's something that often trips people up. So look for a constant, we'll treat it like a step. The first thing that we can do in order to sort of simplify this is we can use the linearity property of a Laplace transform. In essence, we can split this function across the addition, and then we can factor out constants. So this 2 is a constant, we can factor that out front. We can split it across the 5. The 5 is a constant, that can come out front, and we can treat it as a step because, as mentioned previously, it's 0 for time less than 0, and then at time equals 0 it jumps up to 1. Looking at these individual functions, the Laplace transform of a unit step is directly in our Laplace transform table. So we can just go and look that up. So looking at the Laplace transform of a unit step, it's equal to 1 over s. In the other part of our function, we also had t multiplying an exponential. And if we look here, the Laplace transform of t of a unit ramp is 1 over s squared. So we can use both of these. So as we just saw, the Laplace transform of a unit step is 1 over s. Here we have a function t, which we can look up the Laplace transform of, and then we can use the property number 4 of multiplication by an exponential. So the Laplace transform of t is 1 over s squared, and the multiplication by the exponential causes a shift. So everywhere that we have an s will replace by s plus a, where in this case our a is equal to 3. Okay. So there we've got those two properties. Then if we just substitute those back in, we have 2 times 1 over s plus 3 quantity squared, and then we have plus 5 times 1 over s, and that's the Laplace transform of this sort of more complicated function.